Great privilege for me to be able to address you at the start of your studies here at NUS Precies. The university has created a wonderful study environment, and you are about to learn many new things. You will meet many new people, young and old, and you will start exploring knowledge that you didn't even know existed. This is a wonderful thing, and as you go along, you will start to contribute to the body of knowledge that we have built. You will add to the tools of engineering and technology that we have. And that's a wonderful opportunity because technology is everywhere. Technology has shaped the way we live. It has permitted our level of prosperity, our increased life expectancy, our health. It has permitted feeding the increasing populations of the world. It permits easy transportation across the globe and, of course, very easy communication that we experience every day. So you are fortunate that you have the talents and the brains to become part of this worldwide endeavor. It is a privileged position that you have, and I hope you will use it well. But it also brings a level of responsibility and obligations. So today, I would like to ask you at the beginning of your studies to spend a moment, the 1.5 hours that we are here today, to think a bit about responsibility. The word is ethics, and I'll explain what I mean by ethics, and I'll explain why I think you should care. Okay? But before I start discussing this, let me first introduce myself. So I'm a professor at Leiden University in the Netherlands. So the Netherlands, as you know, is in a corner in the European Union, and Leiden, let's see if I can point it. Pointer is not very strong. Is here between Amsterdam and Rotterdam, okay, near the coast. Leiden is home to the oldest university in the Netherlands. This year we celebrate 440 years of our existence, and it has a really interesting history going back to the war between the Netherlands and Spain, but I won't bore you with that today. So this is the building that's shown here on top is the building where the university was originally founded, and it's still used today for all kinds of celebrations. But the science faculty is at the campus outside the center of town in a somewhat more modern and indifferent building, but it houses all the sciences, and it's a great place to be. Can you move forward the slide? Yeah. Okay, so this is a slide showing my experimental group. I'm an experimental physicist. My field of study is nanophysics. So I look at properties of single atoms and single molecules, electron transport, many experiments done at low temperatures, which builds on the tradition of Camerlin-Onnes that I will mention a bit later today. Okay? So now that you know a bit about my background, let's come to the question that we want to discuss. What is ethics, and especially ethics as it relates to science and engineering. Now, I need to make an apology because I've never taught a class on ethics before, and it's certainly not my field of study or specialization. Still, I know from my personal experience that discussing ethics is important. So I'll do it from this perspective. There is no deep historical or theoretical knowledge that I can offer you, but mostly practical. Formally, ethics is a branch of philosophy that discusses what is right and what is wrong and how we know it. But here I will treat it as the set of rules by which we want to or should behave. And now, these rules may not be obvious to everyone, and everyone has its personal set of rules that may be different for others. The set of rules by which we are supposed to live differ between communities, differ between cultures, nations, and also eras, times in the past where sets of rules changed. We will be exploring this a bit, and note that I have my personal set of values. I will not even try to formulate them, but they are important for me, and that's the rules that I try to live by. I will also not try to impose them upon you, but I just want to make you aware that such rules exist and that they are important for everyone. And especially at this moment when you are entering your professional career. Okay. So in order to explore why you should care, I want to do a bit of an experiment, and I want your participation. Okay? So I'll put up a few questions. In some way it may be obvious, and others you may need a bit of time to think. So I'll put up the questions, I'll give you a bit of time to think, and then I'll ask you to raise hands whether you think yes or no, or A, B, or C. Okay? If there's any moment that you want to ask a question or raise a discussion, please do so. Okay? We have several assistants around with microphones, and they can give you the floor if you want. Okay? Let's go to the first one. Now, so the first proposition, the statement that I want to put in front of you is everything that is not forbidden by law is allowed. Okay? I'll give you a moment to think about it, and then I'll ask you to raise your hands if you agree with this statement. After that, I'll ask you again to raise your hands if you disagree with this statement. Okay? So let's first see who agrees with this statement. Everything that's not forbidden by law is allowed. So I will not try to count, but I see about 20 to 30% of hands. Who disagrees? Okay? So it's difficult to count, but I see that there is a large division of opinion here, and that's already a very important point to be aware of. Apparently, you and your neighbor do not expect each other to live by the same rules. Okay? Some of you think that as long as I obey the law, I'm fine, and others think that there are additional rules. Okay? It's already important to be aware of this distinction. Now let's try the next one. Universally accepted ideas about what is good or bad conduct do not exist. Okay? So think a little bit about what is written here. Universal means that everybody agrees around the world and between young and old that there's certain things that is good and certain things that's bad. Okay? So let's first see the hands as those who think that this statement is correct. Universally accepted ideas about what is good or bad conduct do not exist. Can I see your hands, please? Raise them high that I can see them well. All right. I see about half, maybe a little less than half. And then, who thinks that there are such rules that are universally observed? Can I see some hands? Only a few here. Okay? That's interesting. Okay? So, it means that we think that there are rules, perhaps, but at least some of you think there are rules, but not everybody agrees that about which they should be. And as you will immediately conclude, this can form a source of conflict. Because if you think that there is a rule that everybody should live by, or and especially in the context of engineering, I will be discussing, then others may disagree, and it's already good to know that. I have a third one for you. Rules of proper conduct are essential for a properly functioning society. Give it a little thought. If you feel you want to clarify the question or the statement, you need to clarify, then let me know. All right? If not, let's see hands who believes that this is correct, that rules of proper conduct are essential for a properly functioning society. Okay. I see 40-50% of hands. Okay. And so, does that mean the other half disagrees or doesn't know? So let's see who disagrees. I see a few hands. Okay? There is you're hesitating. Yes. Okay. Let's see, because we will have the opportunity to discuss, let's see whether at the end of the lecture you're still hesitating and see whether, what are the points of discussion. But I think this is already a very good start. You're very nicely actively participating. Great. Okay? I'll ask you to be active again in a moment. So, what I will do is I will now become a bit more concrete and start to discuss examples from research practice so that we know actually what kind of things we can encounter. I'll start with a few examples and especially with a few examples that could be already relevant for you in one of the coming few years during your studies. One of the items that you may encounter is questions about publication practices. Now, let me first explain to you a bit about how this works. In research, it is important to make the world aware of what you have done. And one of the important ways of doing this is by, of course, speaking at conferences, but the most important is to write up your results in terms of publications, articles, that you publish preferably in journals with a high reputation, such that people will notice and people will read it. People will refer to it, will cite it, and this will help you in gaining recognition, and this will help you in obtaining positions, in competing for jobs, in obtaining research grants, and so in general, it's very important to publish a lot and publish good work. The Americans sometimes use the phrase publish or perish, right, to emphasize the fact that without publications you're dead, scientifically. Okay. Now, most of these publications that you'll find in the literature are the result of very hard work. But not all. The other day, my colleague Berlier told a very striking story of a piece of work that he had published, that had been literally copied by someone else and published in another journal. Now that is a very exceptional case, but still, you see, research practice is tough. I have seen in my laboratory many experiments fail. Fortunately, I've also had quite a few good ones succeed, otherwise I wouldn't be standing here. But still, what frequently happens is you're trying to get your results, and then at a critical moment, the experimental equipment breaks down, and it needs repair, and it takes a long time. And in the meantime, you're up to speak at the conference, and you don't have the results yet. And for instance, you have a PhD student who needs to finish her thesis, and needs these results. Okay, so when this occurs, how could I rescue the situation? Suppose now my student, say it's a she, she has written 3 successful chapters for her thesis, and she needs a 4th one to complete the thesis and hand in and graduate. Now, you have this problem, the machine broke down, she cannot get the results. Suppose now that my student finds on the internet at a website of a university, let's call it B, University B, she finds a chapter in a thesis of another student who has nearly done the same work. And then she decides to copy that into her own thesis. Okay? Now, the problem that I pose in front of you is the following. How should I respond? So suppose I discover that my student has copied a chapter in her thesis from a source at University B. Okay? What should I do? A, I congratulate her with finding a creative solution to the problem of finishing her thesis in time. Or B, I tell her to change the details such that it is not an exact copy and will not be recognized as such. Or C, I tell her she is fired and should leave the university immediately. Okay? Give it a little thought, and you may also discuss with your neighbors. I'll give you a minute or so to discuss with your neighbors to see what you think would be the proper way of action. Go ahead. I'm glad I see a lot of you discussing, and that's good, because these are questions that perhaps you haven't really thought about before, and you need to shape your opinion. But so I cannot give you much more time, I'm afraid, so let's just see where we stand. Who says A is the right response? Okay, I see 10 hands or so. Who says B is the right response? There's a very large fraction, probably more than 50%. Who says C is the right response? Okay, that's more than A, but much less than C. Okay, well, thank you very much. My response would be neither of the three. So that's not fair, you could say. I haven't given you this option. I would first call the student to my office and interrogate her about her personal views on ethics, what she thinks are the rules by which she's supposed to do science. Because if we're discussing from a different perspective, then it's very difficult to achieve any agreement of proper action. But if she intentionally and knowingly copied the chapter, then I would probably go to C. If she actually did not quite know about what are the proper rules, then I would place the case before the examination committee, and I would propose to give her another chance, to remove the chapter and write an original chapter of her own. So, but we see here that there is quite a difference of opinion, and that it's good to be aware of such differences. Now, in order to continue a bit on this, as I said, the rules of what is proper behavior in terms of copying of text differ a bit per nation, per community, but you will be part of an international community. And the international community is moving towards international rules. So at least it should be good to be aware of such rules. And you can find the rules often stated in the website of professional societies. My personal attitude towards students is never copy anything, not even a paragraph, not even a sentence, unless you put it between quotes and you put the reference to the original source. That can be very useful, of course, because somebody could have said something that you want to quote, because it's important for the line of reasoning that you're developing. But it needs to be clear where the original text came from. Again, that's my personal view, but also you will see that that is more or less what internationally starts to be an accepted practice. Now let's move on to another item. Yes. This is connected again with publication. So, as I said, it's very important to publish a lot. And much work in science is a result of collaboration in a team. Now, there are different expertise, different skills that are usually united in the team. One person is good at theory, another person is good at experiment, another is good at making samples, and this way the team succeeds in doing original work. Now, how much work would be needed in order to deserve being a co-author on a paper? Is it enough if somebody has joined the discussion for half an hour? Is that enough for being co-author on the paper? Well, that perhaps depends, but let me first tell you an anecdote. I want to tell you a few words about George Gamow. George Gamow was a famous Russian scientist. He contributed very important work to nuclear physics and cosmology. And he had written, at some point in his life, he had written a paper with only his name on the paper. Now, what happened is he sends the paper to a journal for publication. The way this works is that at the editorial office of the journal, the editor looks at the paper, looks at what kind of material it is, and he finds specialists to consult and ask whether the paper that has been submitted is valid, original, and deserves to be published in that paper. So these are called referees, and so the paper that Gamow submitted to this journal was sent to referees. And one of the referees responded that the paper was perfectly fine, except for one thing. Gamow, in many places in his text, writes, "We have done this and we have discovered that," whereas there's only a single author. So the referee says he should change this to, "I have done this, I have done that." Okay, the paper goes back to George Gamow, he's allowed to make changes, and the next thing is the paper is resubmitted to the journal and now has two authors. That, of course, also solves the problem, and the paper was accepted. Of course, people started to be interested. Who was this second author? Because he was not known in the community. It turns out it was the name of his cat. George Gamow was a very interesting figure, and he was known for many jokes. So this is one of these special jokes that he made. But the reason for telling you the story is, of course, that it raises the question, how much work is needed in order to deserve to be co-author on a paper? And obviously, the cat did not deserve it. Nowadays, many journals actually require us to provide a list of who has contributed, which of the authors has contributed what to the work, so that it is specified, not just as a list of authors, but whether it is a list that says this author has done this, and this author has done that. So I think it would be a very useful guideline to take that as a starting point for any publication. If you think about the question, well, you have a colleague who claims wants to be an author, then to say, well, okay, let us define exactly what you have contributed to this work. And of course, that can be a matter of debate, and in general is probably useful to be generous then. Okay. In my university, it is common practice, and I believe this is also true here at VC, that also undergraduate students can be authors on papers that, to which they have contributed in the experimental work, and I would very much like to encourage that. In this context, it is interesting to tell you a story of how actually such practice has changed over the years. And this brings me to Heike Kamerling-Onnes, who was a professor in experimental physics at Leiden University. And he worked for 20 years building equipment to achieve very low temperatures. The race that he was then in with his competitor, Lord Kelvin, was to reach temperatures low enough such that helium, the last, what was then thought to be a permanent gas, might become liquid. And in 1908, he succeeded. He succeeded to get a temperature as low as 4 degrees above absolute zero, 4 degrees Kelvin, or in other words, about 270 degrees centigrade below zero. And that created a situation where the laboratory in Leiden had access to temperatures that were so low that many properties of materials could be investigated, and there were many places in the world where they were interested in doing this but didn't have the equipment to do it. So it brought many scientists to Leiden to do experiments. It took until 1923, 15 years, before a second laboratory in Toronto in Canada succeeded in reaching these low temperatures. This work has resulted in the Nobel Prize for Caroline in 1913. Now, in the meantime, Caroline had been working to investigate the properties of materials with his equipment, and he had a student, it's also shown here, Gil Holst. Okay? And they were interested in measuring the resistivity of metals as you cool them down. And it was known that if you take a metal and cool it down, and I'm sure you have learned this in high school, the resistance of the material of the metal drops. The expectation was that the resistance would drop to zero only at reaching zero temperature. So Caroline Onnes puts his student to work, Gil Holst, to measure mercury. Okay? So mercury is of course a liquid metal at room temperature, but if you put it in a tube, you can make it into a wire, and then he measured the resistance of this wire of mercury as a function of temperature, and as it starts at room temperature and drops, he sees the resistance drop and drop and drop and drop just as expected. But then, reaching a temperature of about 4 Kelvin, he sees suddenly that the resistance drops to zero, or at least too small to be measured. Okay, he shows this to Caroline Onnes, and Caroline Onnes says it must be wrong. Right? You must have made a mistake, it's probably short in the wire, measure it again. Okay? So he goes back to the laboratory, measures it again, and it shows the same thing. So Caroline Onnes says, check your experiment again, try again. And it's there. Okay? So then they decide that this is really a completely unexpected property of metals, and this is, of course, what we know today as superconductivity. It's become very important, and it's used in many applications. Quantum computers today are built of superconducting circuits, which we wouldn't have if Caroline Onnes had not discovered that. Well, Caroline Onnes, I say, but his student did the experiment. Caroline Onnes reported the discovery in a presentation to the Royal Academy of Sciences, only with his name. Didn't mention Holst. Now today, we would regard that as unacceptable. We would say the student needs to be on the paper. However, you need to take the habits at the time into consideration, and when asked about this, Holst never complained. He said it was perfectly fine, he had just done what Caroline Onnes told him to do, nothing else. And in fact, Holst did very well for himself. He later became the first director and founder of the Philips Research Laboratories, where there were many discoveries, including the electric shaver and the compact disc. And he has become a very prominent figure in science and technology. Okay. So, speaking about discoveries, let us then come to the next topic, which is patents. Ideas may not have just intellectual value, but actually real monetary value, of course, and this is known as intellectual property that needs to be protected, and the ownership of patents is protected by law. And also, of course, patent laws differ per country, but there are numerous international treaties that between countries that regulate the ownership of intellectual property. Now, for an individual researcher, having patents, owning patents is important. It's not just the net profit. Usually that's not the most important thing. You see, if a patent actually produces revenue, it can be sold, produces some revenues from licensing. Usually, many universities have an agreement that researchers in the university can be co-owner of the patent, but a large part of the revenue goes to the university. But still, mostly a fraction of this money goes to the individual researcher, and that can be attractive. But more important than, for a researcher, more important than this revenue is the prestige. It's a sign of originality, productivity, creativity if you hold many patents, and this again will help you in promotion, in obtaining research grants, and so on. So, then it's clear that if this is so important, then this is again a source of conflict. And research, as I said, is often done in teams. So, if we have a team of people working, in this team, the problems that are encountered in the research are being discussed, then who should own the patent? Is it just one, the person who comes up with the idea finally to solve the problem? Is it some selected members of the team? Or is it the entire team? I'm afraid I cannot provide a good answer, but my personal attitude again is to be generous. And this is colored by an experience that I had during my own studies in Nijmegen in the Netherlands, where this was in the last year of my undergraduate studies, and I was following a course on didactics. Yes, there it goes. Okay? So there's these two vessels that are connected, and this is known internationally, of course, as communicating vessels, and I'm sure in your physics classes you have seen this. If you fill two vessels that are connected, even lower down at the bottom, they will fill up to the same level left and right. Okay? So that's the problem of communicating vessels. Can you advance the slide by one? So, in this course, we were first discussing how to teach communicating vessels, and then in this team of 5 students, we were given the following problem, which is, it looks almost the same, but part of the experiment was shielded by this green panel here. They poured water into the left vessel, and then it turned out that the two levels did not align. Okay? The assignment was to figure out what was actually behind the green panel. So we started discussing, and a few minutes we found out what the answer to the problem could be, and I was sure that I had given the essential idea of what made the solution. And probably you have already seen it flashing by, so could you lower the green panel, advance the slide please. Then this is the solution. They had put the tube into a circle, and there is a cavity filled with air that prevents the two levels to align. Now, why do I tell you this? The discussion that we had with the 5 students was videotaped. And we looked back the video, and whereas I was convinced that I had found the solution, it turned out that already before I spoke out, there was another student who had come up with the essential idea. And that was shocking to me. I had not noticed. And the reason is you're in the middle of a discussion and you're thinking your own thoughts and you pick up some of the sounds and so on. So this has taught me that it's very hard to reconstruct discussions and say, okay, I was the first to give this idea. So keep this in mind because, as I say, it can be a source of conflict, and it's good to be aware that such mechanisms may play a role. Okay, I need to see where I am in the slides. Okay. So my general attitude would be to honor the team. Let's now move on to discussing experimental data. Experiments and data are of critical importance in science and technology. We constantly collect many data, and they play a decisive role in many aspects. So then it's important to carefully think about the process by which we accumulate data. However, we are human. And as humans, we have certain preferences and certain ideas, and these may voluntarily or involuntarily steer the outcome of an experiment and the data. So let me illustrate that with another anecdote from the old laboratory in Leiden. If this will, yeah. So this is Wando de Haas, who was a successor to Kamerlingh Onnes. And so he continued experiments at very low temperatures and continued to be interested in the properties of materials. His special interest at some moment was into the magnetic properties of materials. Now, you're all aware and familiar with ferromagnets, the magnets that you put on your whiteboards and so on. You know that materials like iron can be permanently magnetized, but in fact, all materials are in some form magnetic. Okay. All materials respond to the application of an external magnetic field. And this is what de Haas was investigating. And for this purpose, he had built one of the largest magnets in the world. He's standing there in front of it. And in this magnet, between the north and south poles of this magnet, there was space to put what is known as a cryostat, a vessel that contains the cryogenic liquids, permitting to cool down to very, very low temperatures. Inside that was placed the material in the form of a sample, a single crystal, or a piece of material, and the material was then surrounded by a coil. The coil would pick up the response of the material to the application of the magnetic field. In other words, the magnetic response, the magnetic moment that the material develops. So many materials had been investigated, and typically what was found was that as you increase the magnetic field, as shown on the lower graph, you will see an increase of the magnetic moment of the material, and it can be straight, or it can be slightly curved, and sometimes it can be negative. But this is what he was seeing, investigating, reporting, and interpreting. Then one day, the Haas obtains a single crystal of bismuth. Bismuth is a bit of a special, it's called a semi-metal, but for all practical purposes, you could call it a metal. And he asked his student, Peter van Alphen, to measure the magnetic properties of this single crystal of bismuth. Now what he finds is the following. Yes. So what he finds is the following. The magnetization, as a function of the applied magnetic field, first starts to rise, then it starts to drop, then it starts to rise again. It drops again, as an oscillation. That was completely unexpected. So the Haas says, it cannot be right, must have done something wrong, go back to the laboratory, measure it again. So Van Alphen goes back to the laboratory, measures it again, and finds the same result. So the Haas says, it cannot be right. Check your experiment, try again. So he tries again, same result. Then the Haas decides to take the sample, take the crystal, and put it on a shelf for a year, in the hope that the effect would go away. That, of course, is a very strange response. But it's also a human response, because you get a result that you have no idea where it comes from. No, it's completely unexpected. It doesn't fit into any theory. There was not even a remote piece of theory that could explain the observations that they found there. So, in fact, a few years later, after the publication, this work was picked up by Kapitsa here in Moscow and by Rutenbek in Cambridge, and it became one of the most important tools for investigating the electronic properties of metals, and the effect is explained by quantum mechanics. But the theory was not ready to explain that at the moment that the Haas and Van Alphen made the discovery. So what we learned from this is that it is only human to feel urged to discard unwelcome data. Fortunately, the Haas did not. He almost did by shelving the crystal, but in the end, he decided to report on the measurements as he had found them. Now, in your life as engineers, you will often encounter data that you did not expect. So could you advance the slide, please? Suppose you're measuring, you're testing an engine, yeah? And we're putting the rotation speed along the horizontal axis and the fuel consumption along the vertical axis. And the data points is what you find, and the curve is what you theoretically expect. Okay? So it mostly looks good, except for one point. Now, what should we do with this one point? I'll give you a moment to think, and then I'd like to have, let's see if there's people who would like to give their opinion. There are microphones. Let us see what would be the proper response. So I'll give you a minute to discuss with your neighbors. Does anyone want to propose an action, a response to this problem? Raise your hand high if you want to say something. Don't be afraid, there's no wrong answers that you can give. It's just a discussion, we're trying to form our opinion here. Yes, we have a, could we have a microphone over there?
Thanks. Well, I guess, if I were a scientist, I would like to repeat the experiment itself and find out why the fuel consumption increases at the exact speed.
Excellent. Sounds like a good idea, right? Because this is a bit like the response that we have seen from the Haas and also from Kamerlingh before. You get an unexpected result, and you say, okay, there can be something wrong with the experiment. Let's first eliminate this possibility. Let's repeat the experiment. Okay, excellent. So, but now suppose that the repeated experiment produces the same result. What do we do? Yes, please. Could we have a microphone over here? Excellent.
I think we publish our results and wait for some time for others to find out.
Yes. So, thank you. Does everybody agree with this? Is that a good way to do it? Anyone wants to voice another opinion? Yes, please.
I think we should explore this rotation speed and find why this point is so high.
Yes. So your course of action is, okay, there is a deviating point, we want to find out why. Yeah? Okay. So we have three different ways. I certainly agree with the first. I actually agreed with all three. I think once you've confirmed that the effect is real, then you should definitely publish it. But preferably, you want to publish it with some explanation. Because if there's no explanation, it's not very strong, right? So you want to investigate what's happening. What could happen, for instance, is that the engine starts to have a resonance at this specific rotation speed, and you want to eliminate the possibility of this. So this is the type of investigations that you want to do. But in the end, exactly as you say, the best is to publish it because somebody else will come up with an explanation. Thank you. Now, as I said, data plays a central role in science and engineering, but it also plays a central role in our society. And today, we see a lot of that happening because we have become aware that the concentration of carbon dioxide in the atmosphere is influencing the global climate. And this we know, could you please advance the slide? Thank you. This we know by doing lots of measurements. Here I show, for instance, a compound measurement of the carbon dioxide concentration in the atmosphere. The last part of the curve, where it's shooting up so very high, is the result of actual measurements around the globe of concentrations of CO2 in the atmosphere, and the data that go back to 800,000 years ago have been reconstructed from all kinds of measurements, for instance, from inclusions of small bubbles in ice and so on. So there's a lot of data that go into this. There's a lot of debate about the validity of this data. And the same relates to the actual temperature, the global temperature, because measuring a global temperature is not an easy thing. You cannot put a thermometer anywhere because you want to have the average temperature over the globe. And how do you average? Well, you can't put thermometers everywhere, so you have to have some way of averaging. And so you can imagine that this is a course of lots of debate. And there has been heated debate around the world. I think at this moment, most scientists, or nearly all scientists, have accepted the conclusion that there is a strong relation between the human burning of fuel fossils and production of carbon dioxide and the increasing temperature around the globe, with far-reaching consequences in terms of changing climate and sea level rise. In the Netherlands, we are below sea level already. If the sea level rises another 6 meters, we're seriously in trouble. How could this debate be so heated when it's about data? The point is, of course, that the consequences that these data have, what they mean for what we should do, are so far-reaching that people are not ready to accept this very easily. The same as Van Alten was not ready to accept that the magnetic moment of bismuth would oscillate. And so the first reaction is to push it away, to deny it, to find reasons why it cannot be true. And it's good to be aware of this, but it's also good to be aware that these data play a very important role in our society and the safety of our society. And so that in these debates, your personal interest needs to be accounted for and where possible, be avoided. Okay, I have been discussing a lot. It's a long session, but I want to ask your patience for 2 other items that I want to bring up. And then I want to move to the engineering practice. We've mostly discussed scientific and laboratory practice, publication practice, but now I want to move to engineering practice. In your engineering career, you will likely encounter dilemmas. And then it's good to be aware that there are such dilemmas. And in many cases, matters of ethics, questions of ethics, are much more difficult for us scientists and engineers to resolve than the actual science or engineering problems. An example that I want to bring up from recent years is the following. We live in very densely populated areas, in densely populated cities, and they put a lot of burden on the environment. We rely on our government to provide the infrastructure and the safety for living in these cities. We need supply of electricity, we need effective transportation, we need the garbage to be disposed of, we need clean water, and so on. So there's a complicated infrastructure, and our governments take good care that this works smoothly. Now, there is another role of the government, and that is to protect our safety. And the safety is endangered by the quality of the air. In recent years, or already quite some years ago, we started to be aware that nitrogen oxides are dangerous for our health. So nitrogen oxides is NO and NO2, and together they refer to as NOx, okay, to make it short. Nitrogen oxides affect our respiratory system. They can cause inflammation of the lungs. They can reduce the lung function, and in addition, they nucleate fine particles in the air and the formation of ozone, which further have an effect on our lungs and our health. Now, the major source of these nitrogen oxides is road transportation. So, governments have imposed limits on the concentration of NOx that are regarded as caps, as safe concentrations for living in the city. And they have imposed regulations on car manufacturers such that the exhaust of the cars does not contain high concentrations of NOx. Now the problem comes with diesel engines. And in some way it's a success story because diesel engines have been improved over the years by quite an amount. The efficiency has gone up. And as you will learn about the Carnot cycle, you will understand that the best way to get a higher efficiency is to have the motor operate at a higher temperature. Okay? So this is exactly what engineers have done in order to improve the efficiency of diesel engines. The diesel engines operate at a higher temperature. But what happens at a higher temperature, the diesel engines take in air to burn the fuel, and the air contains not only oxygen that is needed for burning the fuel, but also nitrogen in almost 80% concentration. So at high temperatures, you induce a chemical reaction between nitrogen and oxygen, producing NOx. For the old diesel cars, that was not such a problem because the temperature was low enough that hardly any nitrogen oxides were produced. Now, the car manufacturers found a solution to this problem, and that is they have, can you advance the slide, please? So here's an example. This is a Golf diesel, clean diesel, world's car of the year. They have found that if you spray a product which is called AdBlue into the exhaust pipe, then it catalyzes reaction back from NOx to nitrogen and oxygen, and that solves the problem. So this AdBlue is nothing more than a solution of uranium, so it's a rather simple solution, and it works perfectly. However, it's costly to install it, it's costly to operate it, and the reservoir of this AdBlue needs to be refilled quite frequently. Now, Volkswagen has a very large global share in diesel engines, and they had to find a solution. The solution they found was the following. Can you advance the slide, please? Thank you. So when the car is on the test bench, this is where the government agencies test the exhaust on concentrations of NOx and other pollutants. Now the engineer thought, hey, we can program the computer in the car to detect whether the car is on the test bench. That's not so hard to do because on the test bench, the wheels are turning, but the steering wheel is kept stable, and the GPS does not show that the car is moving. So putting all this information together in a software package, the engineers made an addition to the software such that as soon as the car is on the test bench, it is programmed to inject this AdBlue into the exhaust pipe, and the exhaust is clean. But as soon as the car goes on the road, the system is switched off because it's too expensive, and then the exhaust actually goes up by a factor of 10 to 40. Now, this problem was discovered, it took some time, was discovered 18 September 2015. So that was yesterday, 4 years ago, by the Environmental Protection Agency in the USA. And it had far-reaching consequences for the car manufacturer. Could you advance the slide, please? Thank you. So this is a slide showing a fraction of the cars that the company had to buy back. And they're parked here in an empty spot in the desert. Please move on the slide one more. Here is a list of all the consequences for the company. Well, let's first say that the estimated consequences for the population are, in Europe alone, the estimate is that the increased exhaust of NOx has caused the loss of 44,000 healthy life years. That's of course important. But for the company had to buy back over 11 million cars or had to modify them. That's of course a very expensive operation. Moreover, the company had to reserve more than 4 billion for legal compensations in the USA alone. The engineer held responsible for this work in the United States, James Robert Liang, was put in prison for 4 years and had a fine of $200,000. His boss, Oliver Smith, was imprisoned for 7 years and received a fine of $400,000. Then it turned out that it was not just Volkswagen where this problem surfaced, it was spread more widely, and also Audi company, Porsche, and also some French companies are suspected from similar manipulations. So the head of Audi, Robert Stadler, is arrested in Germany. Head of the motor division of Porsche, Jörg Körner, is arrested in Germany. The stock value of Volkswagen dropped by more than 30% in just a few days. And as a consequence, the shareholders of the company, who have lost a lot of value, claim over 9 billion euros in compensation. In the meantime, many cities around the world have concluded that diesel engines are not going to be good, and this problem cannot be solved, so it's likely the diesel engines will be banned from city centers altogether. So this is all affecting the company very deeply. So what you see here is that it's very difficult to see how the decision-making process within the company went. But it's probably good if at some point during this whole process the company had stood still and thought about the ethics of their operation. Because you can have a certain opinion of what is smart or what is good practice, but we're operating in, especially car manufacturing, is a global operation, a global market. And so you need to take care about how this works around the world. Are there any questions, remarks at this moment before I move to my last subject? I will give you an opportunity for discussion at the end. But let me then wrap up with an example where ethics plays a role in a very modern development. And the development is the development of autonomous self-driving cars. This is a very exciting development, and Mrs. is part of this development. And it's great if you have this opportunity to join them. Cars are packed with sensors and cameras, and the information of all these sensors and cameras is brought together in a powerful computer that is able to steer the car from the starting point to a programmed destination without interference from the driver. But now suppose the car is driving in a narrow lane lined with trees. And suppose at some moment driving in this lane, a child appears from between the trees and crosses the street. What should the car be programmed to do? Save the life of the child or save the life of the driver? This is a dilemma that has been discussed quite a bit, and I would like you to think about it and see what your opinion is. So let's see, which takes preference, the life of the driver or the life of the pedestrian? How should the software be programmed? I'll give you a minute to think about it. Please discuss it with your neighbors. All right, we will have a bit more time for discussion in a moment, but let us see, let us make an inventory how the opinions are divided. So who thinks the life of the pedestrian takes preference? I see maybe 10 hands, a little more, 20, 25. Okay. So who thinks the life of the driver takes preference? That's about the same. So I miss a lot of hands. This means that a lot of people do not know, probably, how to respond, which is understandable. So could anyone of those who didn't raise hands propose another solution, another way out? How should the software be programmed? Please, I see a hand over there. Could we get the back microphone?
Well, I guess the best solution is to have the program which, how to say it right, which tries to save both of them, and the pedestrian, both pedestrian and the driver. Because it's quite ridiculous to give the opportunity for the intelligence, even if it is not the real one. It's quite ridiculous to give the intelligence ability to choose between lives. Both of them are quite equal.
That's a very interesting remark you made. Your voice is very strong. You say it's ridiculous that we allow the program to decide between lives. Okay? There's another hand over there. Could I have the microphone over there?
We cannot say anything about human lives because they both are unavailable. And none of the lives takes preference. So we need our software to be programmed in this way in order to avoid any object. Both these real objects, like a subject, anything, and any person, automatic program should be programmed like avoiding things, any kind of thing. Thanks.
Yeah, so if I try to summarize your remark, which I like very much, is you say we should avoid that we get into this situation to begin with, right? We do not want to make this choice. Okay? Is there any other further comments here? There is a hand over there in the back.
I think we should program our car to save both of lives. I mean, in the car there should be something that would save a driver, and from the outside of the car there should be a thing that would save a pedestrian.
Yes, thank you very much. So you think along the lines of the last two speakers, where you say we don't want to get into this situation where the software needs to take a decision between two lines. That may not be easy, but perhaps it's possible, say, to design the software that it considers scenarios of what may happen in a certain situation. And if one such scenario shows that there might be a child crossing the street, then the car could be programmed to slow its speed such that it could always respond. Of course, consequences could be that the car is driving very slowly through such lanes, and car drivers might not be too happy. But okay, so we've discussed quite a few interesting options. Thank you very much for joining the discussion. So let me conclude. We have discussed a number of ethical problems, and for many of these problems I cannot provide you with answers or rules that you should follow, but it's important to be aware that such rules exist, and that different people hold different values, different rules, and expect others to respect them. And then it's useful during your studies to discuss these amongst you. What do you think is reasonable? How should we act? And look around also in the world. How do other people think about this? At some point in Leiden, I organized a session for students in their final year to discuss problems of ethics, a bit like we are doing here. And I was surprised to discover how many students had already encountered problems of ethics, problems of the kind that they had done a piece of research and their supervisor had just published the work without putting their name on it. Is that an acceptable rule? Is that an acceptable mode of operation? And there were many other things. So be aware that not too far from now you will encounter such problems, and then it's good to know that you need to be informed at least. What is the habit, and where could you go in order to discuss this? Okay. In engineering, you may formulate a bit of a general rule, that is to say that all products as engineering, be it machines, be it procedures, that they should be designed in such a way that they do not do harm to others. My impression is that many of you would agree. But then when you think a little bit about it, it turns out that it's not so easy, because you could have a product that is beneficial to many and harmful to a few. What do you do in this case? Okay. So if you want to learn a bit more about this, could you advance the slide, please? Then I can recommend this book here on the left, The Ethical Engineer, which discusses many more cases that I didn't have the time to discuss today, and also gives a bit of a discussion of, okay, what would be proper engineering practice? Is this rule of not doing harm to others, is that a rule that we can easily observe, and what kind of conflicts could arise? So if you're interested, I advise you to read the book. There's another reference that I would like to give you, which is a YouTube video, which is here on the right, which is a movie. It's an acted situation, a movie made in Leiden, and it's on being a scientist, where in the movie, it's of course an imaginary situation, but where the lives of scientists and students are followed, and there are a number of such conflicting issues arising, and you can see in what kind of painful situations they land. If anything, it's an amusing movie to watch, so feel free to go and see it. With that, I would like to stop and see whether there's any further questions that we could, or remarks that you would like to voice.